Good morning, this is Deep Generative Models. Today we'll talk about the transformers, which is the core technology behind the large language models. Large language models are so important today, not only because ChatGPTs or Google's Geminis are popular. It is also because the large language models are so useful and it is become to couple with every existing technologies. Kind of like computers. Your refrigerators might have a computers, and maybe your TV remote control is having a microcontroller in it. So that's what I mean. So large language model is going to become component or a part of other technologies, even if these technologies may not have close relation to the language model in the past. So for example, let's see a voice clone application. Now this is GPT SOVITS. This is a voice cloning model that is used to clone a person's speech voice. So for example, I'm typing this text and it will transform it into a speech to another person's voice. So this is the original voice.
然后首先我想要对我的资讯内容不够谨慎来道歉，对不起。
She was speaking in Mandarin Chinese, and after I typed this text, and it transformed into
Good morning, this is Deep Generative Models. Today we'll talk about the transformers.
Talk about this text using her voice. So this model has deeply coupled with a language model because this is some kind of text-to-speech model. So if this does not surprise you that its speech is closely related to text, but there were many voice cloning models that does not require any language models embedded in. But now, every latest voice cloning models are usually combined with the language model. And also, this is a video generating models. So the new video generating models, you can usually use a text prompt to control the generation of your video generating models. So this one is the prompt here, and this is the video generated by this prompt. And like this one is one of the popular model that can generate music. Although we can imagine that we can use a language model to generate lyrics. So it definitely requires some language models. However, Suno is able to generate instrumental music. So even if you wish to generate instrumental music, you are going to control it by a text prompt. So it is a trend that all new models are kind of have a language model embedded with it. You cannot just remove this language model. It has become a trend that the latest and the best models cannot work without the language part. So that is how important these language models becomes. And today we are going to talk about the transformer, the core technology behind these language models. So this is our lecture notes. We are going to use this one. We are going to use a lot of materials comes from Stanford seq2seq, the natural language processing and with deep learning. We use a lot of their slides. So we're going to skip a lot of the things here, like the LangChain, API, rig, vector, database, all those kind of things. We'll strictly focus on the model architecture and how and why it works and why it is designed as it is. We have already covered the n-gram generation and the character level language model, and we have discussed about RNN, LSTM, and because we have to introduce the pixel CNN and the pixel RNN. And word-to-vector is one of the important technologies. Word-to-vector is a milestone for language models. It just got the Test of Time award in neural IPS. By using word-to-vector algorithm, you can train a model that learns a vector representation of each word. But we are not going to go into too deep about this because like what we used for the n-gram things. But as you can see, if you are using an n-gram word level model and using an auto-regressive like training, we can train a simple neural network to learn the vector representation of each word. So although they work kind of differently, they have a rough same idea that we use a self-supervised manner to train a model so that we can correlate the word with a vector. You can already imagine how to train models. And the key point is, the important thing is, these trained representation vectors preserve some semantic meanings of the word. A famous example of word-to-vector is when we train the word-to-vector model, and if we get the vector representation of the king, the word of king, and the word of queen, and the word of man, and the word of woman, we can in fact do some arithmetic on the vector space that is corresponded to its meaning, semantic meaning of the word. So in this particular case, you may find that the king subtract the man and plus the woman, and we will get the vector of queen. So let's go back to the lecture note. But now we don't use word-to-vector that much. So I'm going to start with the sequence-to-sequence architecture, because the transformer can be considered as a special case of sequence-to-sequence model. Because we are mostly going to talk about some more subtle and more detailed part of this model, which I think is very interesting. But if you need some big picture about how these models work, and or maybe even if you already have the big picture, I still recommend these two videos made by 3 Blue 1 Brown, because their videos are among top tier videos in YouTube for explaining topics in science and mathematics. So this one is the
for all possible
video.
Next token.
It explains how GPT works in a more general way, and you can have a visualization of what actually happens. And if you have a big picture and some visualization of what's going on, it will help you to understand the importance of the details and the topics we're going to talk about. So let me go to the sequence-to-sequence first. So we are using the slides from Stanford. This slide covers a lot of the RNN and the STM. So we're going to skip them and go straight forward to the part of sequence-to-sequence. The original application of a sequence-to-sequence model is machine translation. So machine translation is quite difficult. We already know that. Although as early as 1950s, people are trying to use a machine to do the translation. But soon they realize it's not that easy. One naive thinking of machine translation is that why not just use a dictionary and replace the words from one language into another. But if you really do so, you will find out that languages are very different. So if you do the dictionary method, you won't get far by using the dictionary method. One of the successful methods is statistical machine translation. Before 2010, the most advanced and promising method for doing machine translation is statistical machine translation. It is a machine learning-based method, and the quality of the translation of statistical machine translation is not that bad if you compare it with other methods, other previous methods like rule-based method, which I mean we have a bunch of different rules written by a human programmer to do the translation. It's mostly because statistical machine translation exploits the benefits of big data. It's more scalable because back then we already have something called the big data. And then the neural machine translation was invented and replaced the statistical machine translation. The architecture used by the neural machine translation is called the sequence-to-sequence model. And soon people find out that the sequence-to-sequence model is very useful outside the usage of machine translation. So what is the sequence-to-sequence model? It is an encoder-to-decoder model. So let's look at the Wikipedia page of sequence-to-sequence model first. So you can see that so there's an interesting trivia about this model, about sequence-to-sequence. In 2023, last year, when the word-to-vector paper was receiving the Test of Time Award for Neural IPS, the author made a public announcement, says that the idea of the sequence-to-sequence translation comes from himself, and was conceived before he joined Google. So he also stated that he mentioned this idea to Elias Saxever and Coquelet and discussed it with them many times. So both of them are the author of the paper, sequence-to-sequence paper. So he accused them, they published this paper without acknowledging him. So the paper is right here, a paper from 2014. A paper from 2014. If we read from the abstract, you can see that it uses a multi-layer LSTM to map the input sequence vector to a dimension and use another LSTM to decode the target sequence. So it is an encoder-decoder architecture, and both the encoder and the decoder are LSTM models. And the main tasks are used on English to French translation task. Okay, so let's look at this diagram of the sequence-to-sequence architecture. So first of all, we have an encoder right here. This is an LSTM, and of course, because it is an RNN, so it takes a sequence as an input. We can take the hidden space as the output. And for a decoder, when using it as the inference time, we can take the output of one step as the input of the next step in the input sequence. So like the autoregressive way to do so. And this model takes the output of the encoder as the initial hidden state. For the implementation, because both of them are LSTM, so the first one can be bidirectional LSTM because we have the knowledge of the input all the time. But for the decoder, we can have only one directional LSTM. Because before we can generate anything, we don't have the knowledge of future currents that has already been generated. So we can only have a one directional LSTM. So basically, it is an encoder-decoder model. Sequence-to-sequence model is an encoder-decoder architecture. And in the original design, it used both LSTM as the encoder and the decoder, and using the last hidden space as the output of encoder. And the output of encoder is used as the initial hidden state of the decoder. And soon people find out that sequence-to-sequence model is very useful outside the machine translation. So many tasks can be phrased as a sequence-to-sequence problem, like summarization, dialogue, parsing, code generation, and not restricted to these applications. There is a GitHub repo for sequence-to-sequence by Google. It contains a lot of different example usage of these models. You can find a lot of different applications for this sequence-to-sequence model, including some image-to-sequence model. Let's move to the transformers and the self-attention. One of the issues about RNN models is that the models works with linear order. So if there has a very large distance between two words or two elements in a sequence, the RNN can be very difficult for an RNN to learn the relation between these two words because the connection between these two words in if you consider unroll the RNN, there will be a very long path because the RNN process the words one by one. Even if we have LSTM, which has a long-term memory, it can reduce the effect of gradient vanish, but still, the link between these two words are very long. So the gradient descent-like algorithm cannot work very effectively. Besides, when doing the generation and or the training, we have to do it one by one. So if we have a very large context of the words, it cannot be trained very efficiently. So why not use attention? So before transformer, people already know what attention is. So people are trying to use attention with sequence-to-sequence models for times. But before we talk about that, what exactly is attention? To describe attention, we have three objects: keys, values, and query. Attentions can be viewed as a soft lookup table. So what is a lookup table? A lookup table is a key value storage. So like the dictionary in your Python, we have many different keys, and each key corresponded to one values. So given a query, we find the most similar or we find the matched keys and retrieving the values corresponding to this key and using this value as the output. One analogy is if you have a box of pens, so you have 12 different colors of pens. So when you wish to draw a blue t-shirt, say a blue t-shirt, you find out the color that is blue. You use the blue color pen to draw and paint the color of the t-shirt. And you wish to draw a red flower, and you pick the red color pen and use this red color pen to draw the flower. So that's the lookup table. So if lookup table is drawing a picture with a finite set of color pens, then attention is like drawing with watercolor. That means maybe you still have 12 different colors, but you are allowed to mix up these colors. So you can have a 30% green mixed up with 70% of red. So for the same example, suppose you are going to draw a blue t-shirt, but you wish this blue to be a little bit lighter toward the lighter blue. So maybe you take 50% of blue and 50% of white and mix them together. Then maybe you think you wish it to be a little bit greener. So you put a little bit green and mix them up. So that is basically what attention does. So by giving a query, we're not just finding one match. We're not just finding one match key. We compute the similarity between this query and every single keys. We find the similarity. And based on this similarity, we compute a weight. The weight that we wish to mix up these colors. Maybe 70% of the first one, 20% of the second one, and 10% of the third one. And we mix them up using the weighted sum and get the output. So that's the mechanism of attention. In the example of language processing, we usually imagine that the attention maps give us the similarity or correspondence between different tokens and words. So how do we actually formula and implement the attention? So the first thing we need to do is to formulate what is the similarity matching and find a way to derive the weighted sum for the similarity. We can actually use any reasonable measurement to measure the similarity between the query and the case. So for example, we can use the cosine similarity. We can use like L2 or L1 distance. All these metrics make sense. However, the most popular one and that is actually used in the attention implementation, in the most attention implementation, is simply use the dot product. So it's kind of like this formula. Although it is written in the matrix multiplication notation, but they are essentially same. So the dot product is pretty similar to cosine similarity, except it doesn't require we to normalize these two factors. So we simply do the dot production. We simply do the dot product without normalize each of them. So after we get this similarity score between these two keys and the queries, we get them for each pair of query. We may have several queries and several keys. And for each query, we compute its similarity towards every case. Then we compute the softmax to get a probability weight. So this formula is the softmax. Then we use this weight to compute the weighted sum of this corresponding value. So let's look at the paper and see the formula. So here is the formula. So you can see that it has a QK multiplication. So which is the pairwise dot product together. And after we get the softmax, we get a probability weight. We get a probability weight and use this weight and multiply it by V using the matrix multiplication. So another meaning of matrix multiplication is the weighted sum. Weighted sum and dot product and the matrix multiplication are all similar and maybe exchangeable concept. A dot product is essentially a weighted sum. And if we have a batch of weighted sum, and it can be represented as a matrix multiplication. Okay, so basically this one is just the dot product to represent the similarity, and using softmax to get a probability weight, then use this weight to compute a weighted sum of the values. The only thing that seems a little bit strange is this guy. What is this guy? It doesn't mention in the above descriptions. This one is introduced by the transformer paper. So the original attention does not have this scale factor. In this paper, it observed a phenomenon that when the dimension of these keys and the queries are getting larger, the value of their dot product is getting larger. So the softmax doesn't work very well with these big values. Recall that we are feeding these values to the exponential if we wish to compute the softmax. And if this is getting bigger and bigger, the exponential will growing up much faster. So that introduces some numerical instability, and when we don't like it, so we are scaling them down according to the dimension of keys, and to make this computation better and more stable. So let's conclude how we calculate the attention. Another thing that we may wish to mention is the multi-head attention. So we call this guy the single head attention. In fact, it has a full name, scaled dot product attention. The dot product refers to the choice of our similarity measurement. We use a dot product to measure the similarity between query and case. And the scale is referred to this variation. We are scaling it according to the dimension of case. But this one is just a single attention, single head attention. So we only compute one type of correlation between say the words or the element of this sequence. They may have different relationship and correlation between words. So because words has many different kind of relations between them, so maybe we want to have multiple attentions to model this behavior. So multi-head attention is a way to do so. So this one is the formula, but we don't look at the formula. We can look at a diagram that is presented here, also in a paper. So on the right side, this one is the single head attention. So let's review it. So first of all, we compute the dot product between Q and K. So it gives a matrix multiplication, but we actually compute the dot product. And because we are using a scale factor, square root of dk. So this one is a scale. And then optionally, we can have a mask. I will go back to this later. It's just that we have a freedom to pick which Q and K pairs that is needed to compute the result. And then we go to the softmax, and finally we compute the weighted sum of V by using the output of softmax as weight. So this is a single head attention. To compute the multi-head attention, first we still have the value, the keys, and the queries. And suppose we wish to compute H different attention maps, then we have H different linear projections for V, K, and Q. The terminology linear projection is used in this paper. So I'm from mathematics background. I know some people in mathematics background doesn't like this terminology because in linear algebra, in many mathematical fields, projection has a very specific meaning. Not every linear map is a projection. It has to satisfy certain conditions and properties. However, the linear projection here is just some linear map. Technically, if we are using the mathematical terms, it is just a linear map, not necessary to be a linear projection. However, this is the terminology it uses in the paper, so we're going to use it because we are describing and discussing this paper. Okay, so for this value, we use H different linear projection to get H different vectors. So these linear projections are trainable. They have trainable weight. And similar for the keys, we have H different linear projections. So similarly, these keys are each of the keys are projected into H different keys, and so is the queries. So at the beginning, we have one set of VKQ, and after this linear projection, we'll have H different set, H separated set of key, value, and query, and so that we can do H parallel single head attention and get H different output. Then we concat all these output together and feed it into a linear map to get our output. So that's the workflow. So that's how multi-head attention compute its output. So since people already know what attention was back to like 2013, and because of the reason that we know RNN is not enough, so a lot of people has already tried to add attention blocks into the sequence-to-sequence architecture. The special part of the transformer is that it discards the RNN architecture entirely and use the attention block only. So if we wish to use the attention map instead of using RNN, what might be the issues we need to solve? So one issue is that the attention doesn't use the position information. So the order of the words. So if we are dealing with a sentence, a sequence of words, attention doesn't care and doesn't use any information of the order of the words. That might get some problem because we know that the order of the words is important in a sentence. We can have totally different meaning if we permute the words in a sentence. So for example, the cat bites the dog has a totally different meaning to the dog bites the cat. But attention only get the attention map, doesn't know the position of the words. So how do we solve it? It is quite simple and straightforward. We add the position information into the input sequence. So for some encoding, we can encode the index into a vector, a sequence of vector. So for each I maybe 1, 2, 3, 4 to n. So each index I, we assign a vector pi to represent the position of that I. So one way to do that, to inject this information into the input sequence, is we concate the input with this position info one by one, position-wise concate them together. However, the most popular way currently is to simply add this position vector into the original sequence. Simply add them together and get a new input. And this seems to work just as well. And so people actually use this method. How do we encode the position? So how do we encode the position? One way to do that is using sine and cosine. We use sine cosine with different periods, and so that each position has a unique representation. This is not too different with the binary encoding of numbers, and it's quite easy to do so. The original transformer proposed in the paper, Attention is All You Need, choose this method. One potential drawback is that this method seems to be quite arbitrary, and as it mentioned here, it is not trainable. So if this doesn't work, we have no way to fix it. So another way to do the encoding is that simply treat these positional vectors as a parameter, a trainable parameters. So we don't care what it is. We simply put into the whole train routine and hope the algorithm, hope our training routine to find out the best position representation for us. So in general, this kind of approach usually gets better result, or at least get something not worse than your carefully designed encoding. However, it has one major drawback, is that it is not extrapolatable, which means suppose in our training, we have only considered the position from 1 to 100. Then it is impossible to extend the sequence into a length of like 101, 102, and 103, because we don't have that position vector. there's no rule to generate new positional vector, so we don't have them. So if we wish to have a longer context, we'll have to fine-tune or retrain the model. But nevertheless, the position issue can be solved by adding the positional information into the input. Another potential issue of the attention map is that even if we stack all these attention maps together, the output is basically some kind of weighted average of the initial input sequence. So why is that? Didn't we have a softmax, and the softmax is nonlinear, right? So the reason is that, let's go back to here and let me erase these kinds of things. So we can see that the only nonlinearity in this diagram is, of course, the softmax. But this softmax doesn't change the fact that the output is simply a weighted average of these input values. So if we stack another attention map above, we are getting a weighted average of a weighted average, and so on. So although these weights are nonlinear, but we still get a weighted average of this value. So that might not be what we want. So how do we solve this issue? The solution is pretty straightforward. We simply add some nonlinearity between two attention maps. So we add some feedforward networks between the attention maps, between the attention blocks. These feedforward are position-wise. So for each position, each of these feedforward network taking just single input, just taking simple word as an input and output to as a token in one position. Because we are usually dealing with a very long and various length of sequence, so we cannot train we definitely cannot train a feedforward network that take multiple elements in this sequence, and it's define the purpose that we wish to use attention blocks only. So the feedforward part is only serve as a way to add the nonlinearity. So another obvious solution is we don't use a full feedforward network. We can simply use like a sigmoid or something. But my impression is that if you are doing so, the modified block may not be as powerful as the transformer block, and you don't get much improvement on the efficiency either. So the last potential issue is the attention maps looks everything at once. But what if we are going to do something in decoder? Because the decoder works kind of like an autoregressive model, so we cannot actually see the future tokens because we haven't generated them already. And in the training, although we know what the future tokens look like, we don't want to see it because in the inference step, we cannot see them. So we want to pretend we don't see them when we are doing the training. So how do we do that? It's simple, we use a mask. It is exactly like what we do the mask convolution in pixel CNN. So if this is something that we cannot see, we simply put the negative infinity as the similarity score. So because this is negative infinity, and after we feeding it into exponential, it is going to get 0, and the output probability will be 0. So by combining all these concerns together, we are getting the design of a attention block. So let's go back to the paper and see the attention block here. So for the encoder, let's get the input sequence here. First of all, we add the positional encoding into the input sequence. And then we do the multi-head attention. And one small consideration is that we are also using some tricks and knowledges to make our architecture more stable. So one popular method to help us to train a deep neural network is to use skip connection. And basically this is a residual block. So we have a skip connection and add the output of the multi-head attention and the original output together. This is a very common used trick to help us training the deep neural networks, and it used here as well. And the other tricks that we use to help us to training a deep neural network is use a normalization layer. The normalization layer chosen here is a layer normalization. It is very similar to the batch normalization, except it doesn't work on a batch, it only works on the layer level. So both of the batch normalization and the layer normalization are popular choices, but they have different strengths and weaknesses. The benefit of using layer normalization is that you have the same procedure for doing normalization in training and in inference time. In batch normalization, we have to collect the running mean and the running variance when we training so that we can do inference without a batch. But the layer normalization doesn't use the batch information, so it doesn't require us to collect those running mean and the running variance informations. Okay, then we give our output into a feed-forward network, and again we're using the skip connection, a ratio network, and using a layer normalization. And for the decoder, similarly, we are injecting the positional encoding into the output sequence and feed it into a multi-head attention. And it also has a residual block like structure and layer normalization. The difference is it is a masked multi-head attention. Both of them are self-attention, but for a decoder, because we cannot see the future tokens, so we have to use the masked multi-head attention. And after this masked attention block, we're using the hidden state and the output of the encoder to do a cross multi-head attention. Note this one doesn't use mask because we are allowed to see the entire input from the input sequence. So there's no need to do the mask. But this one is not a self-attention because the query part is from the decoder, but the keys and the values are from encoder. So they are from different sources. So this one is a cross attention. And again, it has a skip connection and a layer normalization. And finally, we have the same feed-forward network as a linearity. For both of the encoder and the decoder, we have many of these kind of blocks to stack together. And finally, we have a linear map and the softmax map to get our output probability. So since the transformer has been introduced, it gets great performance in various of different fields, assuming we have enough data to train it. And it is very scalable, and it is still one of the best tools in our toolbox. But what are some of the potential issues or drawbacks of transformers? Although transformers are considered to be very efficient, it still needs quadratic computation cost against the length of sequence. So suppose we have a sequence of 50,000 elements or tokens. Because we have to compute the similarity between each pair of query and the keys. So we're going to have like 2.5 trillion storage to record the result of the similarity computed. So that takes time and space to do so. So many improvements are proposed. So people are working on this and try to improve the complexity. However, although they have some success in some tasks, one thing that is the most majority large transformer language models are still using quadratic cost attention. So maybe it still have more benefit than its drawbacks. So, but at least we can say that we still don't have something that can compute things in linear that can replace the transformer that is compute in quadratic cost. And another interesting observation is that although we have a lot of improvement of transformers since 2017, but a lot of them does not have wide success like what transformer is. Most of them can get quite good result in certain tasks, but it turns out maybe in other tasks it doesn't work as well as the original transformer. So transformer is still one of the most useful and powerful architecture we have today. So next time we are going to talk more about the transformer and the GPT models. So next time we are going to talk more about the transformer and the GPT models.